LEDs, or light emitting diodes, they are everywhere. They are typically now the backlight to your smartphones. My car even has LED headlights. LEDs are everywhere now, and they're replacing incandescent bulbs and even fluorescent bulbs because of their efficiency. The problem is, though, for beginner hobbyists, they're actually kind of tricky to power correctly. Now, anyone can just hook one up to a battery and get it to light up, potentially, but there's also a good chance that you're going to burn it out. The reason for that is that LEDs are, it stands for light emitting diode. Diode's the key word here. As you can see, this is the same symbol as a diode symbol, only there's two little arrows pointing away from it, just designating that there's photons of light being given off. But essentially, it's still a diode. Basically, like, you can just pretend that this is an arrow pointing in the direction that current will flow through here. So if you have current trying to flow the other direction, this little wall right here would block it. So that's how you can remember which direction to hook these up in. But anyways, they have something called a forward voltage, and until you reach that forward voltage, the resistance on these is really high. I'm in the order of like 5 to 10 mega ohms, which is 5 to 10 million ohms. So until you reach the forward voltage, which the low end, like a normal red LED, I think is about 1.8 volts. So if you're below that, no current's going to flow, and as soon as you get above 1.8 volts, then the resistance on this drops down to almost zero. So here's a basic circuit. We have a 12 volt battery, and then we got wires connecting this LED up. But here's the problem, though. If you hook it straight to the battery, remember what I said? As soon as the voltage gets above the forward voltage, which we'll pretend in this case is 1.8 volts, the resistance of this LED goes down to almost zero, and that is the same thing as this. So basically you have a battery, and then you have a short. So you're basically just shorting your battery out is kind of what it's like. And this is a pretty decent sized power supply. So if you take a look here, 12 volts times 2 amps, that gives you 24 watts. And if you're shorting it out, that's what you're getting right here, and that will blow out almost instantly. 24 watts is 666 times higher than a typical red LED should run at, and about 363 times higher than what a typical white LED should run at. So red LED is kind of the bottom end of the spectrum. They're typically 1.8 volt forward voltage, which is basically, like I said earlier, the voltage that you have to hit before they'll actually light up and let current flow through them. IMAX, I stands for current when you're talking like circuits and formulas for circuits. 20 milliamps is pretty much going to be the current rating for almost any 5mm LED, regardless of the color, usually. There could be some exceptions. So anyways, if you take volts times amps to get power, you get 36 milliwatts, which is way lower than what that is, hence why this would blow instantly. The white and blue LEDs, the ones that are higher in the visible spectrum, are usually higher in forward voltage. So white or blue LED would be like around 2.8 to 3.3 volts. Same current, so if you take volts times amps, you get 66 milliwatts, which is still, like I said, 363 times less than what you would get across this resistor if you plugged it straight into our 12 volt supply right here. So what you might say is, what if you weren't using a 12 volt supply? What if you had like a little phone charger, like the little 5 volt USB phone chargers? They're usually like 5 volts, 500 milliamps. Wouldn't that survive? No. So we'll do the math. It's 5 volts times half an amp, and you get 2.5 watts. So 2.5 watts is still 69 times more than this value, and it's still 37 times more than this value. So this will still blow, maybe not instantly, but it'll blow very quickly, very, very quickly. It'll get really hot, potentially start smoking, and then it'll give out. So even on a really, what you would consider a light core, wall wart kind of power supply, like the type you would charge your phone with, it is still way too much. And so what you're going to need to do is limit the current going through the resistor to power it correctly. Now, there are some cases where if you use like a coin cell battery, they're not able to produce more than the current required by your LED, so your LED doesn't burn out. And so there's some really rare exceptions like that, but generally speaking, you can't just hook an LED straight up to a battery. So to figure out how we're going to limit the current, well, we're going to use a current limiting resistor. You basically put a resistor in series with your LED and it'll limit the current going to it. So to do that, we're going to use two different laws related to electronics theory. So the first one is Kirchhoff's voltage law, and it just states that the sum of all voltage potentials in a circuit will equal 0. All that's saying is the voltage drops, which would be basically negative voltages. Your voltage is dropping at each point. If you add those up and then add it to your source voltage, you'll end up with 0. Everything cancels itself out. And that's what we're going to use to figure out the voltage drop across our resistor, because we'll need this value when it comes time for Ohm's law. So Ohm's law states that voltage equals current times resistance. And I know it's weird that current is represented by an I. That's just the standard, and it's been that way for, I think, over 100 years. So it's just something that's going to stick around, and you're just going to have to learn that it's I and not C. So voltage equals current times resistance, but this is just a formula. And using basic algebra, you can solve for current or resistance if you'd like. So if you solve for current, you get current equals voltage divided by resistance, or if you solve for resistance, you get resistance equals voltage divided by current. So these are the three ways you'll see Ohm's law written out, and you can use any of these depending on which one of these that you're trying to find. So we have our same circuit here, but now we have a resistor over here that's in series. Now you could have put it after the resistor. It doesn't really matter. It just needs to be in the circuit. So we're going to go with the bright white LED. So it's got 3.3 volt forward voltage and then a current max of 20 milliamps. Now you can go a little above this to maybe 25 or 30 milliamps, but you're going to drastically reduce the lifespan of your LED. So if you absolutely need it to be brighter, you can probably run it at 25 to 30 and it might be okay. But if you want it to last for a long time, you should probably stick to the maximum that the manufacturer specifies in the data sheet. So anyways, 66 milliwatts, that's what we're going to try to hit. So we already know that the forward voltage is 3.3 volts, and the forward voltage and the voltage drop is basically one and the same. They might vary by a tiny little bit in actuality because of tolerances and such, but basically your forward voltage is what your voltage drop is going to be. So remember we talked about Kirchhoff's voltage law? This is basically a 3.3 volt voltage drop. So if it's going down, that's a negative 3.3 volts. So negative 3.3 volts times whatever voltage this that will be across this resistor added to 5 volts should equal 0. So all you have to do is take 5 volts and then subtract the 3.3 from it, and then you get 1.7. So if you take a negative 1.7 voltage drop and a negative 3.3 voltage drop, add those together, you get negative 5 volts. You add that to 5 volts, and that's basically 5 minus 5, and you get 0. So then we know we're good. So anyways, that's how I came up with the 1.7 volts over here. So using Ohm's law, which is volts equals current times resistance, we solve for resistance, so then we get resistance equals volts divided by current. So the voltage is basically the voltage across this resistor, because this is what we're doing the math to find resistance out on. So it's a voltage across the resistor divided by the current max, and I put current max because this is the value that we're plugging into this equation here. So it's basically the current maximum that the manufacturer of your LED states is the maximum. So to get the voltage across the resistor, like I said, we take the source voltage and then we subtract the forward voltage, which is up here. And then that leaves us with 5 volts minus 3.3, which is 1.7 volts. We divide that by the current. We divide that by the current and we get 85 ohms for the resistor value. But before I go on and before I forget, when you do math related to anything with engineering, science, anything, you need to make sure that everything is in the same units. So what I mean here is that since this 1.7 is in volts, this has to be in amps and not milliamps. So if we would have plugged 20 milliamps in over here and not converted it to amps, this would not have come out correctly, and then your circuit would have failed potentially. So you got to make sure to convert everything to the same units, to the same level. So if this were in millivolts, then we could have just used this straight up just use the 20 milliamps here, and we would have been fine. But you just need to make sure you convert everything to the same level. So if you wanted to manually convert 20 milliamps to amps, all you got to do is just divide it by 1,000. So, or if you want to go from like volts or amps down to millivolts or milliamps, you would take it times 1,000. So if you don't want to do all that math and you want a super easy way of doing that, I'm going to show you how. You go to good old Google, and then you put in 20 milliamps to amps. Hit enter. Boom. Google Calculator does the math for you. How easy is that? You don't even need to do anything. And this will work with currency. You can put 20 US dollars to 20 Canadian dollars. You could do distances. You could do all kinds of stuff. You could even do like computer file sizes. You could do megabytes to bytes and crap like that. So Google Calculator is very, very handy. Generally speaking, it's pretty smart, but sometimes you have to spell it all the way out for it to work. So if we put milliamps like that, oh, I guess it still worked. Well, sometimes if you can't get it to work, just spell both the units out all the way. But either way, that shows you that without knowing anything, you can just use Google to translate this stuff for you. So there's no excuse. So anyways, make sure everything is at the same units, and then there you go. 85 ohms is what we need as a resistor right here to run this resistor at the 20 milliamps maximum that the manufacturer recommends. So are we done now? Almost. There's one other thing that we have to consider, and it's the power that this resistor is going to dissipate. If we don't take that into account, there's a chance that the resistor will get really hot and start to smoke, and it could even catch fire. And you want to be careful. And even with the really low volt, low current circuit, that can still catch fire. You'd be surprised. So all we have to do is some really simple math to see what the power dissipated through this resistor is going to be. So this you can really ignore. I just put this here in case you want to see how you would manually figure out the current across this resistor or flowing through the resistor. But we already know what that is because the current flowing through here is going to be the current flowing through here. That's the whole point of a series resistor. You're limiting the current going in this entire loop. So we already calculated this resistor value to get 20 milliamps. So that means that this resistor will be flowing 20 milliamps, as will this, because this is being limited by the resistor. So you really don't need to do the math. We already know that the current across here is 20 milliamps. But if you want to, actually use Ohm's law to figure it out, this is how you do it. So anyways, to figure power, it's just voltage times current. So the power across this resistor, or the power dissipated by this resistor, you take the 1.7 volts across it, and then you take it times the current, which is 20 milliamps, which, like I said, it's going to be the same as the current going through the resistor, because that's the whole point of the resistor. And then we get 0.034 watts, which is the same thing as 34 milliwatts. But like I said, with the whole units thing, since this is in volts and this is in amps, our answer will be in watts. Now, if we had this value as millivolts and this value is milliamps, then the answer would be in milliwatts. It's a really simple concept, but I noticed that a lot of the tutorials and guides out there don't actually mention that, so they kind of assume that you should know that, but that can really trip you up if you don't know that. So I figured that I would go ahead and point that out because that is very, very important. One little miscalculation due to having your units not all at the same level could cause your expensive LED to burn out. So I say expensive. Some LEDs can be expensive, but you know what I mean. So anyways, 34 milliwatts is not that bad. So a 1/4 watt resistor, which is kind of the standard size that most people use for breadboard projects, that's a 1/4 of a watt, which is the same thing as 250 milliwatts. So 34 milliwatts is much lower than 250 milliwatts, so a 1/4 watt resistor would be perfect for this. So basically a resistor would need to be 85 ohms, and it would be a 1/4 watt package, and then that's all you need. You pop this in here, and this LED would power to its maximum brightness and run for the 20,000 hours or whatever the manufacturer rates it at, because you're driving it correctly. So, is this always going to work in every situation? Technically, the math and everything I said is true and it will work. But the problem is it becomes unfeasible at some point. When you get into the really, really, really high power resistors, you're going to run into problems with heat dissipation. So let's do this example here. I went to eBay and just searched for 10 watt LED, and this is the first result. Now technically, if you do the math, 12 volts times 1.05 amps, you're going to get about 12 watts, which is obviously higher than 10, but just bear with me here. This is what I pulled off of the eBay listing. So obviously 12 watts, that is a lot of power dissipated by the LED. So the LED itself is going to have a heat sinking. Even the lower 1 and 2 watt LEDs will need some sort of a heat sink. So keep that in mind. So to power this, usually the closest thing I can think of to power this safely would be a laptop power brick, which 19 volts is pretty common voltage for those, and then most of them will do anywhere from like 4 to 8 amps. So I just kind of went in the middle of the road and said 6 amps. So if you go to like eBay or Amazon and put in like Dell laptop power supply, you'll see that the specs will be in this ballpark. So that's why I chose these two values. So let's do the math to figure out what kind of resistance value we'll need, and more importantly, what kind of power rating will it have to handle the heat dissipation. So just like before, we use Ohm's law. So we take the 19 volts minus the 12 volts voltage drop, and then we are left with 7 volts, which is the voltage that'll be dropping across this resistor. And then we divide that by the current that we're going to run our LED at, and then we end up with 6.67 ohms. So this, again, is unnecessary because we already know the current going through the resistor, because it's going to be the same as the current going through the LED. That's the whole reason we got that value, is because that's what we're going for. So this is just to show you, again, if you want to go through the paces and actually use Ohm's law to figure this value. So anyways, power is volts times current, and then so the power is going to be 7 volts times 1.05 amps, and that means this resistor will be dissipating 7.35 watts. That is a ton. This LED is only dissipating 12 watts. Our resistor is dissipating 7.35. That means this circuit is only 63% efficient. We're almost burning as much energy in this LED as we are in, or this resistor, as we are in this LED. And obviously that is not ideal. So then generally for higher powered stuff, you want to go with a different route. You can use a couple NPN transistors to do like a constant current drive for an LED. You can use an op amp with current sense resistor and let that control the current for you. Let's see, you can use switch mode LED drivers. You can use linear voltage regulators and set them up in constant current mode, which if you pull up datasheet for a linear regulator, kind of like the LM317, and then you scroll at the bottom where they have example circuits, usually one of them will be how you wired up for constant current mode. So that's another method actually to driving these, but the problem with that is it ends up being similar to using a resistor. The bigger your voltage differential is between your source and your voltage drop of your resistor or your forward voltage, the more heat the resistor is going to dissipate, or in that case the linear regulator. So it's still not perfect, but it's a little bit better than using a resistor. But there's lots of ways of doing it, but this was just to show you that whenever you go to the high power stuff, your resistor actually starts dissipating quite a bit of heat. So in this case, you probably wouldn't want to use a 10 watt resistor. It's probably not quite enough. You'd want 15 or 20 watt, and you would definitely want to hook it up to a heatsink. So this circuit is not ideal, but what you can do is try to get this voltage of your source as close as you can to your forward voltage of your LED. You don't want to go exactly to 12. You want a little bit of overhead because you will have problems with stability and some other weird business that can happen. So you want a little bit of overhead, but you don't want to be too far like 19 volts, because then you're going to be dissipating too much power with your resistor. So what about 14 volts? 14 volts is only 2 volts above the forward voltage, so let's do the math. Everything is exactly the same except for the source voltage. So this time our voltage drop is only 2 volts. So the resistance value that we need to get 1.05 amps flowing across this LED is to use a 1.9 ohm resistor. So we get 2 volts times 1.05 amps. this is for the resistor, the resistor's power dissipation will only be 2.1 watts. 2.1 is much better. 2.1 going being dissipated through here versus 12 watts here. That's 86% efficiency. That is much better. And with using a current limiting resistor, it's not going to get too much better than this. So just something to keep in mind. And in this case, you could probably use like a 10 watt resistor and be perfectly fine. You'd still probably want to heat sink it just to be safe, because last thing you want is to build a project that ends up burning your house down. So yeah, that was just an example basically to show you that when you get into the high power stuff, the power part of your calculation you got to be really careful with. Let's say you built this circuit with a 19 volt laptop power supply, and then you got the 6.67 ohms, and then you put in a quarter watt 6.67 ohm resistor here, and then you're like, oh, I'm good to go. You power that thing on, and that LED is immediately going to smoke and potentially burst into flames, and I'm not exaggerating either. So the power part, I've seen a lot of tutorials and guides online of how to power an LED and how to do the math to get the resistance value for the resistor, but about half of them out there seems like they're missing. There's no steps beyond just getting the resistance value. They don't talk about making sure your resistor can dissipate the power safely. So make sure you don't skip this step. You might feel like you're done as soon as you get this resistance value, but make sure you do this and ensure that your resistor is able to dissipate the heat safely. Okay, so grumble. I hate to do this, but sometimes people aren't here to learn about becoming an electrical engineer or even an EE hobbyist. Sometimes there'll be people who are working on a specific project, and they don't want a ton of details. They don't want to learn science and history. They just want a yes or no answer. They just want to get their project done. And so you get on the forums and you ask for help, and then you get a ton of replies from elitists that are like, go read the stickies, go read these 3 books, go take these online courses, and all you need is a yes or no answer sometimes. So this is for the people who are in that boat. This will not be for this will not be for the hobbyist like you and me. This will be more for the person who's just doing a project for school. They're not even an EE. It's just they happen to need to light an LED up, and they just want to know what resistor to use. So for those people, here's some really simple instructions, or in my case, instructions for lazy plebs who don't want to learn math and science. So, step 1, do all your math in the same units. So, for example, don't mix volts with milliamps or etc. Use volts and amps instead. Step 2, subtract your LED's voltage drop from your voltage source. Step 3, take that number and divide it by the max current of your LED to get your resistor value. Step 4, take the result from step 2, which is, your voltage drop, and then take it times the max current to get the power. And then step 5, get a resistor with a power rating higher than the result from this step. And that's it. Pretty simple. So if you don't want to use the formulas and do all that crap, just follow these instructions and you will be golden. So I hate to do that, but I also want to help the people out who just want a really quick answer. So yeah. I guess that's it as far as this part. We'll go to the bench and I will show you basically how to do all this stuff. I'll try to do the exact same examples with similar resistance values and all that, and just show you on the bench that it works. And I'll also show you a little trick for figuring out the forward voltage of an LED if you don't have the data sheet for it, or if you lost it, or you don't have the packaging, or if you're just pulling one out of a huge drawer full of random LEDs. So yeah, let's head to the bench. Okay, so what we have here is a blue LED, and I chose blue because this one actually has the 3.3 volts and it's 20 milliamps, just like the one in our example from earlier. So I have the multimeter hooked across the resistor, which I'm sure looks weird. I have two 47 ohm resistors in series and then a 1K across those two, and that I was able to get exactly 85 ohms to where it works out like in our example. So I don't know if you remember, but when we took the 5 volt supply and subtracted the 3.3
volts forward voltage to get the resistor that's going across the resistor. We got 1.7 volts in our example, and as you can see, we got 1.7. Now, there's really no good way for me to show you, well, here, I guess. Okay, see, the voltage is at 5 volts, and as you can see, I didn't set any current limit on here. This is set to a full 3 amps, so the current limiting is actually being done by our circuit, by that resistor. So it's at 21 milliamps, which it's 1 milliamp off, but you know, the resistor values and everything aren't going to be perfect. And then as you can see, the total power that the circuit's drawing is 107 milliwatts, which would actually be what the resistor is drawing as well as the LED. So I think, I don't remember for sure, I think it was what, like 60 something, like 66 or 70 milliwatts from the LED, and the rest is being dissipated by the resistor. So anyways, I just wanted to show you that when you do the math, everything works great. When you do the math, everything works great. And then one thing I forgot to mention, when you do get your circuit running, assuming it lights up fine and everything seems okay, make sure you touch the resistor and your LEDs to make sure they're not noticeably hot. If they're noticeably hot, like they're getting to the point where it's hard to keep your fingers on them, you might want to go back and double check your math. You know, you're a human being and human beings make mistakes, so it's good to just be safe. I mean, if you're going to make a project for your girlfriend, your family members, coworker, you don't want to hear that your project, because you did the math wrong, caught fire and burned their house down. So I think the goal with everything related to electronics hobby is to not start a fire. Letting the ghost out once in a while is perfectly acceptable, but when you have a final project, you really don't want any of that kind of stuff to happen. So I guess that's it for just showing you the example on the breadboard. I think it is now time to show you my little trick for how to figure out what the forward voltage of an LED is if you don't know it. So what you do is you get your power supply, you set your voltage to about, I'd say about, well, you know what, if you want to be safer, you do 3.6. I don't know if you can see that. Most LEDs won't be much higher than about 3.3. So we'll set it to a little higher than that. But the important part is you set your current to exactly what you're supposed to be running your LED at. So let's say we have this LED right here that we were just using, this blue one that has a 3.3 volt forward voltage. All you got to do is hook it up to your power supply. And obviously you have to have a benchtop power supply to do this, one that has a constant current mode. Constant current mode meaning if whatever you have hooked up ends up drawing more than the limit that you set, it switches from constant voltage mode to constant current mode. So this is what you want. We're going to take advantage of that. So I'm going to go ahead and turn the channel on, the one that we set to 3.6 volts and 20 milliamps limit. There you go. LED lights up nice and bright. Ah, crap. Stupid tripod. There you go. Basically about 3.3, 3.2 forward voltage. So it's actually pretty simple to figure it out if you have a power supply. So I've got a red LED. Hopefully it's not one that I burnt out on purpose earlier. It's going to demonstrate, but I mean, they really don't do... Yeah, that one's already dead. They don't really do anything exciting when you blow them out. They just kind of flash really quickly and then they just stop running. So there you go. Red LED. They're usually 1.8 to 2 volts. This one is a brighter one, so it looks like it's a 2.2 volt forward voltage. Let's try this jumbo-sized. I think it's a 10 millimeter. I can't remember if it's a blue or a bright white. I think it's a bright white. I would imagine this would be closer to 2.8 to 3.3. 2.9. So, yeah, I guess I don't really need to go through and show you every single LED that I have, but you've got a benchtop power supply that has a constant current mode. It's actually pretty easy to figure out what the forward voltage is, but generally speaking, let's say you got a green LED. You can get online and just search for like 5mm green LED, and then you'll find a website like SparkFun or Adafruit or MakerShed, or there's tons of sites out there. You can go to one of those sites that's selling it, and then they'll usually have the information right there on the page that'll say, 20 milliamp forward current, voltage drop, 2.2 volts, and then generally speaking, most LEDs of the same color are really, really close in specs. The only times they'll be a little different is if you get a super bright one. The super bright one sometimes will be a little higher. So anyways, just thought I'd also show you that neat little trick, because if you have a drawer full of LEDs, and then you just pull one out, you're not going to know what the forward voltage is or what the maximum current capability is. So sometimes it's a little tricky, and if you got a benchtop power supply, it is not so bad. And if you don't have a benchtop power supply with the constant current mode, all you got to do is just go to Google and find out. So I tried to be as thorough as I could, and I would really like some positive or negative feedback. Constructive criticism, very welcome, on things I should change, things I could do better, things you think I'm doing fine with how I'm doing my tutorials. And I'll try my best to make the changes, because I just want these to be handy and not to miss any little details that some tutorials out there might be missing. So I know there's a million tutorials out there, but if I had the attitude of, oh, there's already a million tutorials on how to properly wire up an LED, then obviously if everyone had that attitude, there wouldn't be any tutorials out there. So I did this thinking that maybe someone else will find this useful over a different one, and I'm sure there are tons of cases where mine won't be the great one. So whatever. I just want some feedback if anyone is willing to provide it. But yeah, I just hope someone out there, at least one person, finds this helpful someday. So yeah. Okay, so I guess before I go, I forgot to mention that this was just to show you how to do the math to light up one LED. As far as covering other methods of powering, like a higher powered LED using other more complicated circuitry, I might cover that in a future video if I get enough requests. But lighting multiple LEDs correctly is something I'm going to do in the video that should be immediately after this one. So sit tight if that's what you're wanting to do. Now that I've seen tons of tutorials and guides and instructables on that, but I've seen a lot of misinformation on that specific topic. So I'm hoping to clear that up. So keep your eyes peeled for that video. Should come out hopefully today or tomorrow. So anyways, now I'm going for real. See you in the next video.